All right, well, hello everyone. Am I live? I hope this works. Let's check if everything is okay. 1, 2, sound check. All right, well, I hope everything works. And if not, let me know. Should be all good. What we will do today is continue working on Fluke 5700A calibrator build. And last video was working on this board. So I had fixed the problems over here, epoxied the parts. Then I found some actually some damaged PCB on inside layers, and I had fixed those issues in here. I'll show closer in a moment. And also I replaced the connector in here and put the DUI cable. And then the next board which we will be working is this one. So this is in-guard motherboard, and it connects together using the straight pins in here. All right, let's see if video is working. Hopefully it is. Anyway, so hopefully today I can get some of the power on test and check if there are more issues. I'm sure there will be, and work as we go. So I'll just rearrange the video a bit so we can see everything. There we go. So first I'd like to show progress on this board. And for that I'll need some close-up lens. Okay. Now I can show what's going on there. So I had to cut through 4 layers from the top because the wiring, traces in here, they are coming on inner layer 3 and layer 6 and layer 4. So it's 3, 4, and actually 6 and top layer. They are just shield. So I put some jump wires on the internal layers and put some epoxy on top of it. because actually the connection carry 900 volts AC from the transformer winding to the in-guard connectors. I measured the leakage on repair traces, and it was well in normal range, around a couple tenths of nanoamps, so there is no problem with the repair. And I want to put the copper foil on top of this, so it would be shielded as it was originally designed. And then same things goes over here. So the reason why it's like bulging like that, you can actually see it's not exactly flat, because I had to have the enough spacing between the traces. And so there are two traces, you can see like they're going straight up and then going from one point to another and then straight down. But there is, under these top ones, there are some other jump wires. So that was the idea. And this is, so this connector, warning high voltage, J15, connects to transformer, and then traces goes through all this area and fan out on this connector. And then there is nothing really on the bottom. I removed some metal, was trying to get access from the back side, but actually from the top side was more reasonable approach. And then epoxy some of the areas, and then also our last Livestream repair, just put the epoxy on top of it so these wires don't go anywhere and everything is nice and sturdy. All right. And then this connector, it was the original one was still okay, just broken these notches, they were damaged, and I just wanted to make it all nice, like close to original, so I put the new connector in. And also this cable is just the UI cable. I use 34-pin ribbon cable. And this is connection to the rear interface board. Without this cable and without the rear interface board, as we already saw in the last live stream, calibrator will not start. It will give the error that connection is missing. Okay. And my laptop says that there is low charge. Wonder why. Okay, now should be everything okay. Is the sound okay? Check. 1, 2. I think I need another lens for this. Up. Okay. And I actually checked this board already offline, and everything looks okay. So I think we will today we'll go ahead and put transformer in the case, and also start assembling this board in the case as well. But before that, I'll have to do some work on this board. So there was a missing relay, this guy. This is Latchin DS2E SL2 relay. I installed the modern SL2 DC 5 volt Latchin relays. And there is also 22 volt MOV, so I'll have to put that back in. And these relays are original. They are R10 E6297-3 4.5 volts. So they are like standard R10s, but actually the contact pair is shifted, as if you can see. The standard relay pair would be either this two orientations or four, but this one is have two pair of contacts, but it's only in the middle. The modern calibrator use different vendor relays. Those are custom made for this calibrator. And actually I have the replacement new relays, but we'll worry about those later. Hello, Drew. Yes, if somebody was following the last live stream video, there was a problem with the main board. This guy blowing up fuses, and the reason for that was when I connected high voltage connector, high voltage winding from transformer to this connector, then it was almost short circuit, but it was the resistance between this connection and this one was around 12 ohms, and this is 44 volts AC, and there are a couple more windings going to the invert this port. So the problem was when I plugged these two cables from the transformer, there was an overload on transformer and it was drawing too much power and killing the fuse. So that was the reason. And why the short was happening is there was some burned PCB material in this spot and that spot. So I had to cut through 4 or 5 layers, cut all the black PCB damage and restore the connections and put some protective epoxy on top of it. So that was a little bit time consuming, but now it's all should be good. And we will go ahead and start doing assembly tests and power checks. So these two boards interconnect using, you can see this connector and this one, they go right on top of that, like so. And then all the different modules and motherboards, they plug into these DIN connectors. And then the front of the calibrator is from this side, and this is the rear of the calibrator. Transformer stays in here. That's it. So what I'll do now is put the copper foil on top of this stuff, and we will be hopefully done with this board. and we'll move on with doing more testing. And this is some, I think, like maybe 0.2 millimeter thick. So I'll just cut a small patch and solder down in the around edges. Don't think it's necessary, but it's just to keep the original shield in. Just a nice touch, I guess. I also did a little relayout for the lab, and I can have a small tour showing the stuff. That was partially a reason why I couldn't do the live stream yesterday, because I thought I would finish everything together and reassemble the computer, which I use for my related work. But I was too optimistic and couldn't do it in time, so I had to delay for today. I apologize for everyone waiting, but here we are. So this is the new XDevs Lab May edition. Somebody can find even good old time electronics 9823 calibrator, which I will be hopefully putting for a sale soon enough. Then on top of it we have Keysight or Agilent DSO 7000 series scope. Then going to the Keysight E36 312A power supply, triple channel. Then electrometer B2987, Keithley 6485 picoamp meter. Then I have my tech box chair set up with the DUI tech chamber, nanovoltmeter 182M, which is available for sale, one of Keithley 2002s. Then down there, you can barely see it, it's Keithley 2510. We're going back to my reference setup. So on top we have the XDevs Lab cat mascot and thermometer, Agilent airbox, my main references. Those are Fluke 732B, then Fluke 732B charger, and SL 935 resistance standard. Then we have two 3458As, HP 3245, and Fluke 5450 resistance calibrator. Then in the middle we go back to WaveTech 4920M, then 752 reference divider and 732A, the older reference. That's our first calibrator, amplifier for it, and then the rest of the stuff. So hopefully I'll have more time to do some live streams with this new setup. All right. Okay. Any questions? I think we can go ahead and do some soldering. And because everything is moved now, I cannot find some stuff. So I think this stream we will have a lot of time wasted searching for things. Like for example, right now I'm looking for a X-Acto knife. The box on the left of the screen. Left of the screen? You mean down there in the under 2510 shelf? Because that's where is SR 104. And it would be nice if I can clean this blade. Cyclical noise? You mean like relay clicking? Well, this is just a wall. Well, yes. Well, you probably mean right there. And that is indeed SSR 104. Shine some light over there. Stashed away, hidden from any laying around projects. Okay. Oh. Well, actually, I have an article about it on xdevs.com. It's in the reviews area. So any real metrology nut would always have at least one SR104. Alright, so what I'll do, I'll just solder this thing. That should do it. Sorry about the noise. Okay. And the cyclic noise, it's the calibrator running some tests. It's right behind me. No, the fume extractor is not on right now. And also there is one of the voltage references making bad noise because it have the switching power supply in it. Or maybe that's the fan in the laptop. Like right now should be quiet. And then there is noise, right? Otherwise I'm lost and not sure what you're talking about. Okay. And now I'll have to start the fume extractor and we do soldering. Sound check, 1 1. One one. How about now? It's okay. I disable some audio settings. Not sure if that will make any better. Well, now it's working. Okay. Actually, I posted some of the pictures on the PCB work on the EEV blog forum. So if you want to check those out, that would be a good idea. Okay, that looks good. A little patch. I saw some comments on the last live stream saying about the extreme length of it, and I was thinking about either to make short videos about this project or to make like a real-time live streams, and I decided to do the live stream format because, well, there is not much learning from just posting like, oh, okay, here are 20 boards, and then a couple pictures later we have working calibrator. That doesn't really tell the story, how much effort and work is required to bring one of these expensive and high performing units back into service. So, and I would anticipate that there are at least multiple different parts of the live stream that will be needed to get everything to somewhat work in order. Because also due to high price of even used calibrators, there is not much component level repair content. Actually, I like in couple years I couldn't find any detailed information at all. There is something on Chinese BBS forum, 38 HUD, but mostly like just like pictures and like, oh okay, here is the broken part and here is we fixed everything. So doesn't really like give much detail about like project flow. And now this is just normal, some cheap solder, nothing special. Let me show you. It's nothing special. I think it's SN6040 golden solder. There you go. There is no need for special magical solder or anything. This is the particle board. And also another reason why I'm doing long live stream is because, well, first off I can follow the process, like okay, like we fix this module, then we go to the next one, then we go to the next one, instead of just having a bunch of pictures without straight order. And for the viewer it's much easier because you can rewind. So I put an index on the previous video, so if you're particularly interested in one specific part, well, you can just go there and ignore the rest. There's no need to watch whole 4.5 hours. Okay, and this is reasonably okay. Trace repair material. Well, it's not any special material. I just use the piece of the copper single strand wire. So I just take the suitable cable and get a couple strands out of it and solder from one point to another. I did this under the microscope so I can see easier. I think the trace was say 40 mils, but don't quote me on that. It wasn't too thick trace. It's like a similar thickness of the pin from standard 254 millimeter pitch connector, like a cable pin header. That kind of thickness. Okay, so this one. There we go. That should do it. This is not a component level repair, this is board PCB trace level repair. It's a copper head. Little copper head. So all the electrons will stay in place. There we go. Because it's kind of bulging, it's a little bit tricky. I think if you try to order a replacement board from Fluke, this one would cost multiple thousands of dollars. right? Yes, I am. Is the alternative to the Fluke for the calibrators, for the high-end ones? I don't think there is. Essentially, Fluke take care of everybody and bought all the competition. The Tron 4808 would be the closest competitor for the 5700 series, but guess what? The Tron was bought by Fluke in around year 2000. So, and shortly after, they killed the Tron calibrators line and also killed very nice the Tron benchtop multimeter 1281, 1271 and similar units. And in case of the Tron multimeters, they are reincarnated as Fluke 8508 reference multimeter, and well, to this year there is a successor for the 8508, which is 8555 and 8588. But essentially those are legacy of Datron. I contacted Fluke before with a quotation request about the new multimeters, but well, they decided to ignore my request and didn't reply anything. So, so much for that one. We're almost done here. I think this is it. My professional activities. Well, I work at EVGA here in Taiwan, where we have design center, and my work involves design of computer hardware like graphic cards and motherboards and some other special projects. So if you Google up VGA card like Kimpin series of the recent version is RTX 2080 Ti Kimpin edition, so you can Google that one up, and I was doing the concept and hardware design and a lot of testing for that product. And also similar lineup is motherboards, Dark series, that's the marketing name, for Intel CPUs. So that is X299 Dark and Z390 Dark. You can Google those up and you will find these are already launched products. That's why I can talk about them. But obviously I cannot say much about like details on design and things like that. But what I can say is you can go to xdevs.com and go to the guides section, and there you can find OC guides or technical guides where I can describe some of the details about different features and how I get design for higher performance. So if you have a particular question, feel free to ask and I'll try my best to answer. Okay. Let's measure resistances to make sure that we didn't do anything stupid. There you go. Yep, it's all good. Now our work with this board is, I would say, done for now. And let's move on to the next. We don't need copper foil anymore. Hi Matthew. Will the... Yes, it will. That's as much as I can tell you. Let's call all this copper foil parts out. So here doesn't look too bad. Just some dust. This is also 6-layer PCB, and this is analog board which take care of all the interconnects and all the control for all those expensive and special PCBAs. So on this board I have to put them off in there, and I think that's it. I don't see any other issues. This cable goes to the front connectors of the calibrator. Have a lot of wires. Also the other cable, this guy, goes to the rear connection. It is cut, so this will have to be repaired, but we will worry about that on the later date, maybe on part number 5 or 6, something like that. So I already bought them off. This is the guy which we need. Got it from DigiKey, and I need only one, but as usual I buy spares and spares of the spares just in case, and they are not that expensive, so I bought 10. This is varistor, 22 volts, 800 amps, 7mm disc. Original one is smaller, I think, but it should be alright. Oops. So let's get that guy in. Some stuff is falling out. The purpose of this varistor is to protect output. I believe it takes care of sense line, but I'm not sure. I need to check on schematics. And there it is. Yeah, Ernest, the high precision test equipment is my home hobby, so everything you see in my videos pretty much just for my own self-education, and this is at home in here. So first I wanted, basically everything started like 10 years ago. I really wanted a benchtop DMM, so like with all those like nice functions and math, and able to measure resistance and voltages to good precision. So I bought a broken meter, and then I figured out, okay, it's not so easy to fix them, because it was Keithley 2001, and there was no schematics, and it was 4-layer PCB, like actually 2 PCBs, digital PCB and analog PCB. So I started learning like, okay, how things work in it, and start reverse engineering schematics. So basically I look at the components and then trace all the connections and then draw the schematics of the result and try to understand what each part does. And then, well, I started to design my own voltage reference, do different things to experiment with. And well, after I got the meter working, that took me like a couple years, but I learned a lot in the process, and that's the main reason why I do it. And also the main reason why I try to publish everything on my website. So young engineers who are interested in precision analog design, they would have a resource to learn from, because that's how I learn. And also you would think like, oh, this is 30-year-old design, or like that meter is 30-year-old design. So like today in the modern world of digital electronics, you would not think that, oh, this is useful or something. But actually in analog and in measurements equipment, like all of the theory and all of the design ideas pretty much valid even today. So you can learn a lot if you don't neglect that fact. So yeah, you can find a lot of new digital designs like FPGAs and high-speed processing stuff, but in the end our world is analog, and converting analog signal like temperature or voltage or power or frequency like oscillation signals and all that, still handled by analog first, and then you convert into the data, and then you can do the processing in digital. But to do the accurate conversion, it's take a lot of challenge and a lot of work. And this isn't really industrial. I'm sorry about the focus. Because industrial usually like high power stuff and like motors and like big grunty things for the most of the applications. Like, but here this is everything pretty much just home, usual apartment, and that's it. It's not much industrial here, and it's also metrology is rather clean. Like you want the calibrator clean as possible, and it's not involving like working with a lot of hazardous materials or other nasty things that you would need special dedicated lab for. Okay, so it's all good. Let's start assembling things into case. Get the fume extractor out of the way. So we don't need this anymore. And well, not really. There is no financial return on this, because like even this project, the build of the calibrator, I spent thousands and thousands just to get these dead parts to work with. And if I would be running like calibration business, like that's what most of the applications for these calibrators is, I would need to like spend like maybe half a year or so, and doing the full time every day, like calibrations for customers and everything, and that's just not happening. And actually I don't want to do that because that's not why I do it. I do it to learn and to educate myself on precision designs and analog design. So the like necessarily return of investment is not the goal here. And like another reason why I do it, I over the last couple years I managed to get to know and also meet great people who work in this industry and somewhat related. And also we started some nice and interesting collaborations together. So that's another fun part, that you get to know people who are really great engineers, and there is a small but very nice community around this. And I even created the chat box on XDev server. It's using good old school IRC. So you can just go to xdevs.com chat and there is always somebody around that's somewhat related to electronics, and too often we have people who have also into this as a hobby or even as a job and doing different work related to electronics design. See, this is just nasty. Yuck. Alright, let's put the transformer back in. Hi Adrian. Yep, it's been a while. I also bought a replacement fans, so I think we will install these. Here's one. Here's another one. These are a bit lower. Actually, one of them is 2.1 watts and another one is 1.3 watts. I want this calibrator a little bit quieter, so I think I'll use a slower speed fan on one of the sides. And these are Sunon. Let me show you. There you go. Sunon maglev fan. There is a model number ME92252V1000UA99, 24 volt fan. Very nice. Original fan still working, but I just like, when we spend so much effort into this project, kind of like fan is like 10 USD, so why not make a nice brand new fans. So I'll have to rig these connectors back onto the new fans. But that will not be a problem. So this is the slower one. And this one is the faster one. I put in the faster fan on the side where the power regulators are. So those usually run quite warm, around like 65 C. So I think they would need a little bit more cooling power. And this is the wrong screwdriver. But guess what? I don't know where is the right one. So also, like, well, I guess I have to deal with the I'm not sure where is the yet another screw. I guess we can install it later. Oh well. Oops. I think we will do. So these crimped connectors, 3-pin connector. I could buy a connector and do some crimping, but well, that would be a lot of effort for this one-off job. So what I'll do is just merge this cable and yep, that would be good enough. Not very professional, but this is just home project. She'll be all right. Is the audio okay? No problems now? I think that should be enough. Okay, great. I can put the wide angle lens, so if you guys interested to see me, I don't think they have much value. Okay. I don't think showing how to cut two wires on the fence and reconnect them to the cable with the connector is very advanced topic. Just part of the job. Nasty. Well, the problem with connectors of this type, usually that you need the expensive crimp tool to make it like really nice. And since I'm doing this, like I don't use this connector anywhere, so that would be buy an expensive tool for like one-time use pretty much. And that's not really financially reasonable for the home lab, because these tools, like the proper tools for crimping connectors, can be like hundreds and hundreds of dollars. They aren't cheap. There we go. That should be it. All right. There's our little cute cable. Let's do the second one. put the thermal shrink tube. Here we go. Alright. Like a bot one. Well, almost. And now we use the special patented heat shrink tube sealer. There we go. Okay, that part is done. Let's get all the dust on the floor. And now we're ready to go. Let me change the lens. Okay. Up. Mm-hmm. I think it goes from the top. Yeah, definitely goes from the top. There we go. Let's secure it in place. Fluke box where all the Fluke parts live. And it's all the way up there. Each. That's not it. Should be back with screws. This is all back with electronic parts. I think this will be enough for now. We'll have to find rest of the screws later. These are 632, those pesky imperial units. Actually, the frame is a little bit bent. Yes, and there was a broken screw in here. You can see bits of it. And actually I need to get that thing together. tough to fix. Alright, let's worry about that later. Alright, let's see how the board goes. Okay, so this hole isn't aligned. Not too bad. Not too bad, but why? Okay. Much better now. I think this will be okay. But I still need those screws, because actually there are different length screws going all the way here. Oh, found the short ones. That's a progress. Not the box. Nope. Much longer screw goes in there. And actually it should be too fast on screwing everything down, because this board goes second. The other board goes first. Like that. Oh, I think the battery's out. Time for the next one. Guess I should eventually buy a proper camera for doing this kind of stuff instead of using DSLR. There we go. Here we are, big box. I think we will need some of these and some of those. And just random parts and things. Like a candy bar box. Yes, of course I did make boards for my own projects. Not as much and as many as I would like to. But yep, I did different 4-layer boards. Okay. And at work I did different boards together with some other people support. We did up to 16 layers, and I like making different layouts and playing with the different parts. So it's a lot of fun, and it's not as hard as one may think. I would definitely recommend trying and designing your own stuff, even if it failed first. You still learn a lot, and next time you do better. There is design technique: fail first, fail fast, and it's great for learning things around electronics, because even if you know theory in great detail, it does not replace the real world hands-on application. You can design perfect piece and perfect circuit in theory and in simulator, but on the first power on it will explode and release all kind of smoke. And that is part of the why we do the prototypes and why we test things in hardware. There is no way around it. Okay, I think there is longer screw in here, here and here. I still need a couple more long screws. At least Fluke use the same size on all the locations, just different length. And normally there is a protecting shield, metal shield comes on top of this board, and there is also protection shield on that board. I don't have those, so I'll have to design some replacement and order the PCB in there, or not PCB but metal shield sheet. There we go. And yeah, I think this is it. And I'll put those 3 screws later. And these ones, I don't remember what oh, I remember now. Those to hold the retention bracket for the high voltage assembly, which I don't have, and which I will not be putting in this calibrator. Okay, this is good enough. Oh boy. Now I remember what I forget. This. I forget this. This is the fiber optic interface cable between that board and this board. Well, at least I know that all the screws come in. And, well, it's time to remove something. Or maybe I can just squeeze it in. Can I? Maybe I can. Let's see. Is it in? Didn't hear a click. Usually there is a click. Yeah, I think I can get in. Yay! It's a little bit hard to reach in there, but not impossible. Hold the tone at the right angle. Yeah. Almost got it. So we go. Yeah. Oh yeah. That was a click. That one didn't click. Now let's connect all the cables. I wish I could show this. basically. There we go. That header goes right in there. Like so. This is our fan. And this is our cable goes in there. There we go. Nice and tidy. No problem. Now we put the other side, which is a little bit congested there. So we have 3 cables going in, and yeah, I'll need to do this off camera. I see now it will be tricky to put everything together. With the fan installed. Well, I guess I can remove the fan, and they have designed nice 4 holes, so you can actually remove the fan without removing the frame, which was nice system design. Designed for easy access and fast repair. And there is our fan. See? And now we have much easier access to work with. This connector plugged in. That one is in, and this one. All nice in place. Now we have our mains filter, which we need 2 screws. Where this one goes. And there is a post in there. Oh boy. That will be hard to reach. With the board installed. Yeah, it will be a real pain. Yeah, I think I still need to remove the board. Yeah. Okay. Just need a little bit more access in there. A little bit more. Yep, that should do it. That should do it. Yeah. What? This screw is too long, too short? Okay. Connector is in place. Nice and secure. Also, I want to zip tie this fiber. Let's do that. Because it can be jammed in the transformer, between the transformer and between the PCB, and that would not be very well. Yep, this is good. All right. Everything aligns so far. Nope. Okay. Board is nice and secured. Now it's time to put the fan back. All connected. Any questions, guys? You are quiet ones. Or anybody is waiting for the magic smoke to release? Alright, fan is installed. I guess we can plug out guard boards and see what happens. That's the power supply board, and that's the CPU board. They're plugged like that, back to back. And you can see all this empty area is because it's facing the transformer. So it just slides right in. And then all these heat sinks, they're right in front of the fan, so all those regulators will be nice and cool. And board is in. Here's the CPU board. Nice and steady. Okay. See? Guess we can connect the front panel and see what happens. But before that, I'll need some pads so we don't damage stuff on the back. Like so. I think I need a bigger one. Yeah, this will not work. This maybe will work. Let's do this face. This is the front panel. I already put the VFD interface board, so I'll not reconnect all the wires. We are way too early for that. So let's plug the interface. Connect this one so it doesn't flap in the breeze. This is wideband output, but we don't care about that at this point. And here she goes. This is interesting. All right. We need more screws. This time these are flatheads. And then the side screw. And these are just short ones. What the hell? Huh? Nowhere to go? Still need longer ones. Yeah, this one is too long. I need something in between. And this one is too short. Just basically want to keep the front panel in spot so it doesn't move around and we don't damage our expensive display. That's basically the idea. I'll be having new front panel after everything else is finished. This is how you doing? Okay. Oops. Well, I think this is good enough for now. What caused the original traces to fail? That's a good question. I don't really know. But I would think just maybe like it was used in the or stored in the humid environment, and then somebody tried to apply to turn it on, and high voltage went there and caused damage. But I don't really know. Oh boy. Now it's kind of start to get heavy. So I think we can power on and see what happens. But before that, we will need to connect the rear board, which is this guy. That's the rear PCB. So let's connect it. And because I don't have the rear end, I'll have to let it flap in the breeze like that. And we can go ahead and connect some power supply boards. Particularly this one. It's one of my other boards from previous calibrator, and have a hole. There was PCB damage, so I had to repair that and cut the PCB material out. See? Can shine some light. And there we go. Whoop. That's it. And jump fire some stuff. But now this section, that's the high voltage regulator to generate plus and minus 380 volts. All this section. So let me show you where it goes. There we go. There we go. So the purpose of this board, it takes the AC from transformer, goes through the connectors between the A4 and A3 and A4 boards, and then this board rectify all those AC voltages and provide unfiltered, unstabilized DC output. And then the second board, which is this one, this board takes those DC voltages and regulate to stable DC levels. This large heatsink, these are LT1033, LT1085, LM309, LM309, and smaller ones. Those are regulators to generate DC voltages used in the calibrator. And actually there is one heatsink missing. I think I need to put that in. Give me a second. If I can find the heatsink part. Maybe I'll... I don't think I can find it anytime soon, so we'll just go ahead and plug it in. There you have it. So there is also behind this shield, this is actually a cover that directs the airflow. The fan is right here. Maybe I can lift the camera so you can see better. So the fan is direct airflow, takes from the back and then directs through the boards. So there are this board, get the airflow from the fan, and then there is PA board, power amplifier, 2 high voltage boards in here, then AC voltage boards, then DAC. It's right here in the dead zone. There is no fan and airflow is very minimal. Then you have 2 resistance boards and switch matrix board and current board, and then 2 front boards in the beginning. In the face is wideband option. So this would be, now this is the minimal configuration. We will check all the power, make sure everything's okay. And there is also a rear board right in here, hanging on the 2 cables because I don't have the metal work that it's normally mounted to. Alright, let's turn it on and see what happens. Let's check the main switch is correct. Yes. Okay. And let's see if there is something. Oh yeah. The fans are working. No smoke. And you cannot really see anything because the display is very dark. Let's see if I can turn off some light. Display is working, so that's already a good sign. There we are. Let's turn it off. We can move it a little bit better. Up. And maybe something to lift it up. Is that reflection there? There we go. I think this should be better. Okay. Now I have everything is really dark, so you can see the screen better. So here we are. First signs of life. Okay. So we can do instrument config, show hardware. So the main board revision is J, InGuard is B. J is the base 5700 series config. Installed assemblies, rear panel, and that's it. It's 5700A. Because we don't have any other modules, so there is nothing else to show here. We can show instrument setup. So there are format EEPROM, that's to erase all the calibration data. Let's see, okay. Calibration interval, you can set different 24 hours, 90 days, 180 days. Internal clock, still okay. It's held by the, wow, this is really hard. Okay. Amplifier type, so you can select different amplifiers. And remote port setup, GPIB or RS232. I use GPIB. And we can do self-test, self-diag, front panel test. It's essentially key test, knob test, bell test, display test. You can see all on. This is, lights up all the displays in the right VFD. Left VFD, sorry, all off, no problems. Memory test is passed. Then we can do display control, all on. So this test, this one, all off, no problem. Column test, no problem. Crosshair, no problem. And we can do diagnostics. And it will say a lot of errors because there is no board installed. So we can plug some boards and see what happens next. First we put deck board. You see now the frame is bent because the board doesn't follow the guides very well. I'll have to squeeze it a little. Okay, now 2 more boards. If I can find them. Okay, this is switch matrix board. And that's the current board. Okay, and PA board. The PA board, it's actually missing the cover. So I can show you the overview. Of everything in here. So we have power supply, in-guard interface and DC power supply, PA, that's the oscillator A13 output board, that's the oscillator reference, that's the deck board, that's resistance working board, resistance calibration board, that's the switch matrix board, and this is current and oscillator assembly. And then we have the front panel. So there are missing 2 boards in here. One board is A15 and A16, A15 and A14. Those boards handle high voltage 1 kilovolt range and 2.2 amp current range. And there is also 2 boards that goes in here. These are wideband option. but we will not be installing those in this calibrator, because first they are optional, so it actually can do most of the functions without those. And the second reason is I already have those boards installed in my main calibrator, which sits right over there, this guy. So I don't actually need those boards if I want to have just main functions on this second unit. So let's turn it on and see what happens and run some self-test. But before that, I want to put a cover on top of it, so the airflow is directed through the board. And for that, I'll just use one of the cover from the other instrument, from the 3458A. But it doesn't really fit that well, so I'll guess, well, nope, scrap that idea. This one. The cover just a little bit damaged, just a little. How's she looking? Or maybe just put these two sheets like that. It should be good enough. Yeah, come on. There we go. Now I need to turn off the lights because the screen is real dark. But before that, I forgot to put the relays in. Let's do that. That's those three relays I was showing in the beginning of the live stream. brand new ones. There's a brand new relay. It cost about 20 USD for one piece. And I bought some. Like I said before, spares of the spares for the spares. And most of the boards in this calibrator are from 1991, 1992, and I guess a few boards are 1989. So yes, this calibrator is around 30 years old already. But actually brand new Fluke 5730, the design is essentially half of the boards, they are same as this one, and other half of the boards they are using the same ideas but just using the modern SMT parts, and instead of old digital logic they use modern Altera FPGAs like Cyclone series, but essentially that's the same thing other than the new fancy LCD front panel and like USB interface and stuff like that. But all the analog stuff, all the real important precision stuff is exactly the same. And if you compare the spec of 5720, which is designed around 1990, and the spec of the 5730, you will see the difference is only on the few functions and few ranges, like mostly high voltage AC and wideband option. That's where the most improvement was done on the 5730. All the DC, all the resistance functions, they are very same as the 5720. There is no difference in functions and in the stability and accuracy. Okay. Relays are in, and let's power this beast up. Okay, it's much quieter than the first one, that's for sure. Let's see if all the boards are detected. Instrument config, show hardware, go hardware config. So let me zoom in and try to get rid of the flicker. Well, sorry about the flicker, it's because of the VFD refresh rate. Calibrator in my set, it was older than one I'm working on. You mean the one I have already? The first one? The one I showed you before among the other instruments? No, that one is newer. That one is actually most of the modules in that is 5720, and most of them are 1995 or so. So that is basically upgraded version of this one. But they are very close. They are like essentially 95% the same thing. And yeah, they are close. The design about this one is designed originally in 1987, 1988, and 5720 was improved version of it, which is essentially for better reliability, better spec, so they used better parts in it, but it's basically essentially selecting for the better performing parts. Schematic and design is almost the same. I think I have plans to actually upgrade this one to 5720 as well. So I'll work on the modules and upgrade, so there will be some future live streams that we can check how we can improve the performance of this one. But first we need to make the base function of this and all the base ranges working to the spec as they expected. So let's go over and check that all the modules detected. So current module, ohms, high-res ohms oscillator, rear panel, switching matrix, DC voltage, AC 220 volts. Yeah, everything seems okay. Let's do the self-test. Now there will be 2 errors, I think, should be, which will be related to missing board which we have. But all the other boards should, yes, A14, we don't have this board. So it should say 8255 control board. This is the interface chip which is on that board. So okay, continue test. And it will ignore all the related functions for that module and test all the other modules. That is okay. So for this test, calibrator will use its own reference and all the diagnostic circuits and run through the functions, run through the ranges, and check if the measured signal output is indeed the specification tolerances for the self-test point. And then it runs through all the different modules test and gives you the, if there is any error, it will give you error code. You can check those error codes from the service manual. And how to calibrate the calibrator, I think that will be a topic for some other video. And one of the main benefits of Fluke 5700 series that you can do the simplified calibration using only 3 references. That is 10 volt reference, 1 ohm reference, and 10 kilo ohm reference. That's why these calibrators are so desired for home hobbyist application and like enthusiasts like me. So you don't need actually to have whole calibration lab to test everything, and you can do the simplified version of calibration which will adjust all the functions and ranges according to that, which is very handy. 5700 is not warmed up, so yeah, like normally you would want to have this calibrator run for like 30 minutes or at least a couple hours, so you can do like make sure all the assemblies are stabilized and reach their working temperature. But because we are not really care about that at this point, we can just continue. Now you would think like, oh, okay, like I fix the motherboards and then go straight ahead and plug all the modules I have. And that is because I already actually checked the power before. So I know that there is no major like explosions and anything like that expected. So that's why I went ahead and straight put all the boards in. But actually, if you are just doing the unknown calibrator or any actually other test equipment troubleshooting, you would want to first check the power without all the modules installed. So like if there is, like for example, over voltage condition because of the regulator that's broken, then you don't fry all the other equipment and all the other expensive hardware in it. You would want to keep minimum possible for the power test, and then as you progress through the troubleshooting and build up the confidence, you plug more modules, more options, and test things together. So it's testing right now AC high resolution oscillator. Then different parts of oscillator, circuitry, analog, digital, control. This self-test is actually taking about 15 to 20 minutes. And it's pretty comprehensive, so very handy for the diagnostics and troubleshooting. You can hear some relays clicking. That's like as the calibrator progresses through the different test conditions, it will select and switch different functions and ranges. So there are a lot of relays on each of these boards, and well, it's like a music. It's a precision calibrator music. Sound of clicking relays. Now I know for the fact that at least one of these boards is bad, which is A7 board, current board. It passed self-test, at least that's what it was doing in the other calibrator, but it had a drift around 400 ppm per hour, so that's way outside of the spec. The spec should be like a couple ppm within one day, but it's many hundred times over that. So we'll be troubleshooting that sometime in future as well. Hopefully my friend Todd can send me some packages, and one of those packages will include brand new front panel with the brand new display board, so we can replace this ugly looking front panel with a nice looking fresh face. That will be real joy. Okay, this is an interesting one. 10 ohm check fault. Well, actually 10 ohm resistance network in this calibrator is broken. So we'll just continue on this one. You can see much more relay clicking because it's essentially selecting, during this test, it's selecting each of those, I think 19 available resistances. Yep, that is expected. Any questions, guys? Assembly A14 is not responding. Well, of course it's not responding because it's not there. Continue. A14 again. 5700 diagnostics are done. Well, that's a good result so far. Didn't get any other errors, so that's looking good. Let's do another test, which is do the calibration for the 0. And if you try to calibrate too fast, it will give you a warning. Calibrator has only been on 13 minutes. Do you still want to calibrate it? The reason for this message is you need to wait for the warm-up time, so all the circuitry inside settle to the stable temperatures. So then the calibrator will get the valid accuracy. If you do it without warm-up, then you will have large error because the ovens didn't get the stabilized time yet, and you will get less than optimal performance. There is little Easter egg. When you run the calibrations, there are little funny symbols in the running animation. It's like a ball, like an animal, like a I think train, and then car. It's kind of fun. So DC0 is calibrator applying short internally and doing the 0 adjustment for DC ranges, for the current ranges, to get the correct null. No, you don't need 4-wire short externally. It's using internal short on the A9 board. It's recommended to run this DC0 calibration every 30 days or so, so you always maintain the correct 0. And remember, still have all the output connectors still hanging in here. They are actually not connected to the front terminals. Current 0 may fail on this error, on this step. I'm not sure. No, it's okay. Right into the memory, and yay! DC0 calibration is complete. Now we can do much more difficult test, which is do the calcheck. So the calcheck is the function inside of the 5700 series that essentially runs almost complete calibration, but instead of using external sources for reference, it uses internal source, internal DC reference and internal 10 kilo ohm resistance and 1 ohm resistance standards, and do all the calibration for the unit internally. So also the difference is that during the calcheck, it will not override the calibration constants, but just measure the difference between the current measured accuracy and what those constants are stored from the real calibration before. So you can give, for example, if you run this you maybe calibrate the calibrator externally like every 1 year is a typical cycle, but you can do the calcheck even every day, and then you can monitor stability of the function and stability of the ranges of the calibrator, and make sure that there is no sudden changes or failures occur between the calibration cycle periods. And I think all the dates, yes, this is the default main calibration. Main calibration was done at January 1st, 1988. That's the default value. So all the constants, they are completely gone, erased. So there is no calibration values in this calibrator. So it doesn't really matter. But what matters is we can run this test and perform like a sanity check if the main functions operating correctly. First it asks you what's the present ambient temperature, so we have 24 degrees here, and then it does the check. So this full check takes about 1 hour, and I think it will be failing much sooner than that. Because I know that at least we have 10 ohm resistor failure, and the current assembly is drifting a lot, and I didn't test much of the other assemblies, so yeah, I think this will fail. I'll be greatly surprised if it's not. And actually, for fun, we can start the same test on my other calibrator. Let me move the camera so you can try and see both of them. I'm not sure how this will work. There we go. Can I get both of them in focus? Yeah, I think this is reasonably okay. Maybe like that. So we can do the calcheck 24C and test start. I think after this calibrator somewhat working, I'll find a spot right in here. So there will be two of them together. Well, actually, a tour in my lab would be nice. I actually already did the tour earlier today in this stream, so you can just go back and see. I think it was within first like 30 minutes or so. And for the calibration, we'll be using that and that, which is, this is 10 volt source. You can see it in these 2 meters. It's hard to see, but it's minus 10, 0, 0, 0, 0, 0, 5, 6 volts. And that meter connected together shows almost the same value. And then that is 1 ohm, 1 ohm and 10 kilo ohm overnight resistor. That's the prototype. And this is another calibrator. It's resistance standard, so you can generate short 1 ohm, 10 ohm, 100 ohm, 1k, 10k, up to 100 mega ohm, and also 1.9 multiplier of those values, like for example 1 kilo ohm and then 1.9 kilo ohm. So essentially this calibrator is the resistance function of the 5700 series. And Fluke had first 5440, 5450 resistance calibrator and 5200. That's the AC calibrator. And then they designed and combined all those 3 instruments into 5700 series models. So that's regarding the Fluke calibrators. And of course they had some older models like 330 series. Those are DC calibrators, and I'm not sure which model was for the AC older than 5200 series. And then these are my 2 reference meters, Keithley 3458As. They are very stable and very nice. I use them for all my reference measurements. And that's the AC standard. So that's like AC voltmeter, but 7.5 digit, and essentially competitor for the Fluke 5790A and 5790B. So to test the calibrator, I'll use 2 of these and use 752 divider, and also use the AC standard to make sure this function and all the ranges working correctly. What else I can show? And then this box right in here, it's a booster for the 1 kilovolt AC voltage range, and also gives 11 amp AC and DC current range. Right now it's turned off because it's quite noisy. It has big 120 millimeter size fan and making a lot of grunt and noise. So usually I turn it on a day before I need it. Like for example, to calibrate multimeter, like Agilent 34401, very typical 6.5 digit benchtop meter. I'll turn this guy on day before, then do the calibration next day, and then turn it off afterwards. I turn on like a day before, so it have enough time to stabilize and get everything nice and ready for work. Still running AC volt convergence, 2.2 volts, 10 hertz, and this guy is running AC voltage, 2.2 volt gain check. Didn't fail yet, so that is good. I'm looking down on the screen with the chat box. Now, like in the winter, these calibrators are real nice and cozy because they have the fan exhausting warm air from the side. It's also the reason why I place this calibrator in this area, so all the exhaust going in that direction, and it's not warming up these meters. You need to think about thermal management when you place instruments like that in the rack, to make sure that the warm and hot instruments will not heat up precision standards and will not make them give you a bigger error. Because with the precision metrology equipment, temperature is very important. Because even if you warm up like even 2 degrees warmer, then all your values will shift as well, because there is no ideal resistor or no ideal voltage reference. It's always affected by the temperature. You don't want too cold, you don't want too hot, and you want to have the same temperature as was done during the calibration test. Actually, these calibrators are not that hard to calibrate if you have the proper equipment. And for example, if we say, how do you calibrate the calibrator's DC 10 volt range, let's say 11 volt range, which is have accuracy specification 2.3 ppm. So you can use either calibrated within 90 days 3458A, which have better spec, like this meter, or you use, like mostly what is used is DC voltage standard, like this one, which have annual calibration and have the spec much better than 2.3 ppms. So you can transfer 10 volt from there to 10 volt into the calibrator, and you use the null-meter, like the instrument right in here, like this thing. This is get focus right. This is Keithley 155, one of the best null meters available. It's nice little cute box. So don't be fooled by the analog display. This is old instrument, but it's very useful for transferring two DC voltages between each other. So you use, for example, you know the 10 volt calibration standard, like for example this one. This is Fluke 732A. So you calibrate the standard. Let's say you have 10.10 volts within like 2 ppm accuracy, and you want to transfer to unknown voltage, like 10 volt from the calibrator, and you want to compare them. So you use this little cute Keithley, or there is another instrument like Fluke 8845, which is the same thing, just different design. And you use the sensitive range, like this range. This instrument goes, let me show you. You have maximum range 1000 volts right in there, but nobody using this kind of instrument at 1000 volts. You go all the way to the other end of the dial. So the most sensitive range is 1 microvolt. So you have the full scale deflection 1 microvolt. So essentially you can detect very small, like nanovolt range deviations between these input terminals. So you connect grounds of the calibrator and your known standard together, and then you connect one side of the standard to the one terminal, another side of the calibrator to another terminal, and you measure how many microvolts difference is existing between those two instruments. using this nanovolt meter, and it's using battery power. So this is important, as you don't have any leakage or any noise picked up from the mains power. So essentially this instrument is very sensitive detector for the zero. That's what it's very useful for. Oh. And it's a very nice bit of kit. You can search for one on eBay, but the good working condition, those are not cheap, and sometimes they go for as much as like 500 USD or even more. Bit of a special kit. And the similar approach exists also for resistance test. For that you use bridge, and you will compare output of the calibrator and output of the calibrated resistance standard, like for example ESI SR104, and you will compare what's the difference between those two standards, or to the calibrator and the standard, and using the same current, same cables, same settings, everything, so you can estimate what's the error of the calibrator. It's a bit more complicated for the AC voltage, but the idea is the same. You use AC standard, or you use transfer standard like Fluke 792A, and you transfer known standard to the unknown calibrator. Still running. AC voltage convergence 22 volts, 300 kilohertz. And this guy is running 22 volts, 900 kilohertz, and now it's 1 megahertz. And when it's doing the calibration check, actually front inputs are not connected to anything, they're completely open. So you can see this cable going on. It's connected to my 10 kilo ohm standard, because I was doing some checks earlier, and that's the reason why it's all interconnected. And this is the 10 volt cable going from over there. And I'll also monitor temperature in the lab using Fluke 1529 over there. So you can monitor and log like what's the ambient temperature, to make sure if I get like, for example, 1 ppm off, I can check if that's because the temperature is become a little bit different, or is it because some other reason. Any more questions? Testing 22 volts, and this guy is testing 2.2 flatness. So far so good. Still running. Yeah, about the soldering station, I think I'll buy one eventually. Probably for the part 3, maybe, on this guy. Because I expect we will need a lot of changing relays and components, and all of those boards are through-hole, so we will need ability to quickly remove stuff and test components, do fun things like that. Well, am I doing anything useful? I designed a couple things, so I'll be actually getting one project out of the way, hopefully within next couple weeks. And also I buy test equipment from eBay, like broken things, like pretty much 90% of this calibrator, and actually that one as well, is bought as a parts from eBay over last I think 3 years. And I decide like, okay, I'll just buy different boards, broken boards, and try to make a calibrator and make something fixed together. So that's how I ended up with that one after about 2 years, and now I'm spending time on second one, which is much sooner because I already know a lot. And I'd say most of the reason why I'm doing this is to self-educate and learn things about precision electronics, how to design high performance analog circuits. So that's knowledge not very easy to find online, and that's essentially a content to publish on my website xdevs.com, where I try to document everything, take a lot of pictures of the calibrators, of the standards. Pretty much same thing happened to these 2 meters. I bought them as broken parts and spend a lot of effort to restore them to the fully working order. And you can, for example, for this 3458A, you can go to the xdevs.com /fix/HP3458A and see a very lengthy article. Okay, here is the error. 22 volt AC flat diverge. Error code 2604, reset the instrument to continue. So it failed. You can zoom in and show. And with the calcheck, you cannot continue when the error happens. So the only way is to reset and start over. So you basically get the error, you troubleshoot the module, and after that you test it again, and if it passes, you maybe fail on the other point, or it passes. So we can maybe try again, but I'm pretty sure that we will not be able to do anything. 24, enter. Yes, I do have a day job, which is completely unrelated to precision analog stuff. And the camera battery is out, Sorry about this. I think my microphone battery will die out soon too. Maybe I should change that before it happens. And let me change the lens. Okay, here we go. So my day job is essentially digital and power electronics. I design computer motherboard and VGA card. You can just Google TIN or Ilya Tsemenko and EVGA and you will find a bunch of stuff. So yes, it's not metrology related, so there is no conflict of interest between my job and my hobby. So everybody happy. I don't think this is very exciting for now, so probably we should finish up this video and maybe time for last minute question. Anyone? I think this is kind of shorter video than the last time. Let's see how long. 3 hours and 34 minutes. Yeah, I see Todd in the chat, so let's everybody welcome Todd. Without him, I think many of these XDevs projects would not be possible. He's a mastermind behind many things. So welcome Todd, and I hope for some packages soon enough. At least this calibrator indeed does hope for the new front panel. Just look on how broken this one is. There are like buttons and keys destroyed and all that. Yeah. One other thing I wanted to show is, let's reset this. What I like about these calibrators, let's say we want to output 10 volts. So 10 volt, enter. So you see 10 volt, separate. And you can read actually the spec of the unit. So you can read 24 hour, 23 degrees plus minus 5 C specified. And certainty is plus minus 3.8 ppm. That is, if it's calibrated to the reference standard, within 0 days. So if we have go back instrument setup and change calibration interval to let's say 1 year, done seeing this, so you can do check the spec, and for 1 year specifications 8.4 ppm. So you can read all the specifications and all the uncertainty of the calibrator from every function, every range, and you can also read this by GPIB. So it's simplify test procedure. So instead of calculating all the uncertainties for each point, you can just read it from the calibrator, already calculated for you. And we can do the same for the other functions, like for example 10 kilo ohm, and then specification would be 14 ppms. It's very handy. And also, if you, let's say we have the 10 kilo ohm, because this is unlike 5500 series, you can, like if your real DMM shows, let's say 10.0002, then it will already give you error after you enter the value displayed on DMM. So in this case, it's 20 ppm. It's very handy. And also for the AC functions, the same thing applies. So you have one 10 volts, 1 kilohertz, and you have the spec, 92 ppms, and then you have the offsets. It will show you how much off you are. You're welcome about the article on 3457A. That was one of the less than detailed articles, but it was very nice one, and I think that was not even my work. I was just supporting and providing the place. Yeah, I have no idea about 5101B. Never looked into those. The problem with my location in Taiwan is expensive shipping. So I cannot buy like big and heavy stuff, and shipping of that, even if I get it for free, would be prohibitive. What about own design of the calibrator? Well, if you want to do like simple kind of spec, maybe like 4.5 digit or even 5.5 digit, that would be possible using off-the-shelf parts. But if you want to design something like even 6.5 digits, then it will be very expensive, very fast. It's already expensive even if I rebuild this 5700 series calibrator using Fluke parts, or most of them like Fluke boards, and just doing the component level repairs. Even this is already thousands and thousands of dollars. Imagine if you have to design all of those precision parts and custom resistors, or even order like from Vishay, like one resistor network. I can show some of them if I can find any in the reach. Let's say this one. So yeah, let me focus. This is a resistor network, essentially two precision resistors in the one package. designed designed in 2002. So the top resistor is 16. Let me zoom in if you can see. Where's the focus? Yeah, it's 16 kilo ohm and 1.3 kilo ohm. So just if you want to make this part, which is not the highest stability or highest performance, it's still very good network. But if you just want to make like 10 of these, it will cost you a couple $100, and you will have to wait for at least maybe like half a year or so to get your order from Vishay Precision Group. Oh, this is an interesting error. We didn't see this one before. Some of the resistors I bought before, they cost $250 for one piece. That one was 1 mega ohm, 0.4 ppm per degree temperature stability, and I believe 4 ppm annual stability. So that was 247, if I recall correctly. Yeah, for one resistor. Alright, I think that's a good progress for now, and now it's given a lot of errors, so we will be doing troubleshooting and testing. So you can find a lot of information about projects like this on my website xdevs.com, and well, hopefully I'll see you some time in the future on this channel or in my next video. Thanks for watching, everybody, and bye.